Yeah, I'll just do that. Okay, we're recording now.
All right, everyone, let's get started. Hi, Ari. Hello. So welcome everyone to our final honors defense of the season. I'm super excited to present Ari. He's been doing this stuff for like almost a year and a half, I guess now. Yeah, it's a lot of background in this project. And so, similar to the other honors presentations, we'll have, I think, 35 minutes of presentation from Ari. And then, we'll open it up to questions from the audience. Then we'll kick you guys out. And then the committee will grill them some more. And then we'll go from there. All right, so yeah, it is my great pleasure to present for you Ari and his project on transformations of bound quivers. Let's welcome Ari.
All right, thank you for the introduction, Yari. I won't lollygag at the beginning because we have a lot of background information to talk about. So before we get into the content, here's a little outline of what we're going to be thinking about today. We're going to start with, like I said, a lot of background. We're going to go over the basics of quivers and their representations. We'll talk about bound quivers, and then we'll connect those two ideas combinatorially with this thing called the Auslander-Writing quiver. Now that we have the background knowledge after that section, we're going to talk about some motivation building up to the main question that I've been working on for the past year, 6 months, something like that. And then afterwards, we will present my results from two different perspectives. The first, a combinatorial framing, and the second, an algebraic, more constructive framing. So first of all, what is a quiver? Well, a quiver is a collection of points, which we call Q0, if we're calling our quiver Q, and it's also a collection of arrows between those points, which we'll denote Q1. And we'll write the quiver Q as an ordered pair of those two things, Q0 and Q1. The graph theorists here might notice that this is the same definition as a directed graph, or even a directed multigraph with self-loops, and that is true, but we're going to shy away from using that terminology in this talk. And we'll also only be looking at quivers without multiple edges and without directed loops. So two examples of the types of quivers we'll be looking at are shown right here, both with 4 vertices, but this one right here has 4 arrows and this one only has 3 arrows. Now, we can imagine these diagrams as being indicative of a system of linear maps, vector spaces. But before we talk about how we do that, I first need to say that on this slide, and for the rest of this talk, the letter K will denote some arbitrary fixed algebraically closed base field that we'll be working over. So a representation, which will usually denote M of a quiver, is an assignment to each vertex, a vector space, and to each arrow, a linear map between corresponding vector spaces at the beginning and tail of that arrow. And again, we're going to write this as an ordered pair where these MIs denote these vector spaces at each vertex, and these phi alphas denote the linear maps at each arrow. A couple of examples we can see here, looking at these quivers that we saw on the last slide. Here we've got one-dimensional space, two-dimensional space, one-dimensional space, and another zero-dimensional space, along with corresponding linear maps. Maybe they're just 0, or maybe they look more like matrices. In this case, we have a 1 by 2 and 2 by 1. And on the other hand, over here, we have all one-dimensional spaces, but we can still just have any sort of zero-dimensional linear map going between these spaces. Before we get into the more of the math that we're doing, we need to stop and talk about some notation, because quivers are very often very large diagrams. And so writing down a specific representation as this diagram is usually impossible to fit on a presentation slide like this. So what we're going to do is we're going to come up with this shorthand notation, where we're going to take the labels of the vertices of our quiver, and we're going to write them in a stack corresponding to these two rules. If the dimension of the vector space at vertex I is n, then we're going to write I n times in this stack. And if there's a non-zero map from the vector space at vertex I to the vector space at vertex j, then we're going to write j below I. That's probably really confusing, so let's look at some examples. Let's work with this quiver again that we've seen on the last couple of slides. And let's look at this representation. We can see here at vertex 1 and 2, we have 2 one-dimensional spaces. And so 1 and 2 are written each 1 time in this little shorthand notation corresponding to the one-dimensional spaces at those vertices. On the other hand, vertex 4 is a 2-dimensional space, so 4 is written 2 times. And then 3 is 0-dimensional, so 3 is written 0 times. We can also see that there are 2 non-zero maps in this representation, going from vertices 1 to 2, which corresponds to 2 being below 1, and from vertex 1 to 4, which corresponds to 4 being below 1. And we have a very similar thing going on over here. We have a one-dimensional space everywhere, so every vertex gets written one time, and the order from top to bottom of this stack of numbers just follows the flow of these non-zero maps. With these objects, representations, we can do all sorts of familiar operations. What's probably the most important one, especially for this talk, is this thing called a direct sum. This is a way of taking two representations of the same quiver and combining them to get a new representation. And the way that this works is that we fix some vertex, we look at the vector spaces at each of our, at that vertex in each of our representations, we take the sum of those two vector spaces and we put that at that corresponding vertex in our new representation. That's what this means. You're taking this vector space and this vector space and summing it. And then we look at corresponding arrows in these two representations, and we look at the linear maps corresponding to those arrows, and we just stick them in a big 2x2 block matrix to make sure that the dimensions all work out. For example, let's look at these two representations of this quiver. I've highlighted them in different colors to make the next step more clear. What we're going to do when we take this direct sum is we're going to combine this space with this space with this space, and finally this space with this space. And we can see that happening right here. And then we have to take care of the linear maps. What we do is we just, again, like I said before, stick them in a 2x2 block matrix. This ends up here, this ends up here, and the same thing going over here. There's a little bit of a redundancy here. We can remove this row of zeros from this matrix and we can combine these down to make this a 3-dimensional space and a 2-dimensional space and a 1-dimensional space. And generally we'll just skip to that step of it. If you give me a pair of representations, a common question that we might ask is how they're similar and how they're different. And the tool that we use to distinguish these similarities and differences, these things called morphisms of representations. If you've taken linear algebra, you can just think of this like a homomorphism of representations. How this works is we're going to relate corresponding vector spaces in two representations of the same quiver by connecting them with a linear map. For example, if we have this representation M and this representation N, then we have these vector spaces corresponding to the same vertex, and we're going to connect those vector spaces with one of these blue maps, which indicate one of the linear maps coming from our morphism, which is a collection of linear maps. And then we're also going to enforce an additional condition, which is that each of these squares commutes. That is, if you compose these linear maps, and then you compose these linear maps, what you get is the same thing. If you give me some fixed quiver, let's call it Q, and we look at all the possible representations of Q and all possible morphisms between those representations, what this forms is something called a category, which will denote rep Q. A category consists of two classes. We have a class of objects, and we have a class of morphisms. And you've probably seen an example of a category before, even if you didn't know it. If you've taken abstract algebra, you've definitely heard of a group. There's a category of groups in which the objects are groups and the morphisms are group homomorphisms. A slightly weirder example is the category of sets, where the objects are sets and the morphisms are functions between those sets. And finally, most importantly to us, is the category of all representations of some given quiver, whose objects are these representations and morphisms are just the morphisms we defined on the last slide. The idea here is that if we just look at the objects, it's kind of like this jumbled up, unordered list without any structure to it. But once we add in these morphisms, these directed relationships, it gives it a skeleton, a backbone to work with. So earlier we talked about this operation called the direct sum, which allows us to combine two representations. And I think the natural question to ask after learning about the direct sum is to ask when you can decompose a representation into the direct sum of two other representations. If we can do that, we're going to call our representation decomposable. If we cannot do that, we're going to refer to that representation as indecomposable, meaning it cannot be written as the sum of two other non-zero representations. And very importantly, if you give me any representation that isn't indecomposable, I can break it down into a sum of indecomposable representations, which sum up to get us this original one. And even more importantly, this decomposition is unique. There is exactly one way to do this for any given representation. And what this uniqueness tells us is that these indecomposable sums completely characterize our original representation. If we look at some property of our original representation, then because this decomposition is unique, that property must necessarily be split apart and divided evenly among these indecomposable sums. And we have a very similar idea.
Does order matter in that sum?
No, it's up to isomorphism. We have a very similar idea for morphisms. Morphism, which cannot be written as the composition of two others, is something that we call irreducible. And it's the same idea as before. It's just an object that cannot be broken up. So in this little toy example, you can see that this arrow from X to Y is basically the same, is doing the same thing as doing this arrow and then this arrow. And so we would say that this arrow is kind of like the composition of these two. On the other hand, this arrow and this arrow, those cannot be written as the composition of two other arrows in this little diagram. So those would be irreducible. Now, there's an alternative way of looking at these objects. And before I get into this, I should say that these next few slides, this section is going to get pretty technical. And if you get lost, don't worry about it, because we're going to tie it back together at the end with a nice bit of motivation that follows from all of this. So we have an alternative way of looking at these objects using this object called the path algebra. We're going to denote that KQ. And what this is two things. It's a vector space over K, whose basis set is the set of all paths in our quiver. But it's also a ring with multiplication structure between basis elements given by the concatenation of paths in our quiver. For example, you look at this quiver right here with 3 vertices and 3 arrows, we can see that we have 3 length 1 paths. These are just the single arrows in this diagram. And we can combine these length 1 paths to make a single length 2 path, which is right here, alpha gamma. You'll notice that we can't combine something like alpha and beta because the end of alpha does not line up with the start of beta. And so when you try to put those together, you don't really get anything that's meaningful. So we define that to be 0. And if you look in this basis set that I've written over here, you'll also see that there are these 3 other paths that aren't really obvious in this diagram. These are what we call the lazy paths. They're length 0 paths at each vertex in our quiver. And the reason we put these in here is because we want this algebra to be unital as a ring. We want it to have a multiplicative identity to make some math work out nicer and easy. Make math work out nicer later. Sometimes when something that looks like a quiver or a representation of a quiver occurs naturally in other fields of math, we're not necessarily interested in all possible representations that we could build off of that diagram, only a subset that follow a specific set of rules. For example, something that shows up a lot is this thing called a commuting square, in which we have 4 objects. In our case, we're going to think about them as vector spaces, and then 4 maps going between these. And in order to make this commute, what we want is that when we compose the maps corresponding to these arrows, what we're going to get is the same as what we did as composing these maps corresponding to these arrows. And this is something we saw earlier when we were talking about morphisms. We wanted each of those squares to commute. But we can write this down as a set of rules on this diagram saying that this path in the path algebra is equal to this path in the path algebra. And you can see this rule right here. But for reasons that we'll see on the next slide, we prefer to have this in the form of a 0 relation. That is, we want a linear combination of basis elements of the path algebra being set equal to 0. And so instead, we're going to prefer a notation that looks like this. Another example is this thing called a chain complex, in which any 2 successive maps combine to be 0. And we can write that down just like this. There's no need for rearranging since we're already just setting something equal to 0. When we place these rules onto a quiver, we're then going to call them bound quivers. But I've always thought that this was a little weird because there's a tension between the fact that you're looking at this diagram and it's saying, all right, well, this path exists. Alpha beta is real. It's here in this diagram. But then you look at the rule and it says, you have to ignore that. That doesn't exist. And so these are more concisely and formally defined using the path algebra. What we do is we take this set of 0 relations that are the rules that we're enforcing onto the path structure of our quiver, and we set those to be the generators of some ideal inside of our path algebra. And then we just quotient out by that ideal. And what that does is it creates an algebra whose multiplication structure is in some way indicative of the path structure of this quiver with that bound enforced upon it. And that's why we want them to look like 0 relations, because that's what the generators of an ideal do. But it's still not really clear how exactly this path algebra relates to the actual representations of our quiver. That's what we wanted to get at in the first place. And so we have this very nice theorem that says that the category of representations of Q is equivalent. You can think of this like an isomorphism of categories to the category of modules. These are these algebraic constructions that we can make from a ring over the path algebra AQ. And so this allows us to very smoothly and easily and without loss of information travel between making these arguments about these very combinatorial geometric objects that are representations and these very algebraic abstract objects that are modules. But we can do even better. We can say that if you give me any finite dimensional with the addition that's associative algebra, we can find some bound quiver whose bound quiver algebra is has an equivalent module category to that arbitrary finite dimensional algebra that we started with. And what this tells us is that the study of bound quiver representations subsumes the study of modules of these finite dimensional associative algebras. If you don't know what that means, don't worry about it. All you need to, you just need to trust me when I say that a lot of things are the modules of finite dimensional associative algebras. So a lot of things in math can be reduced to questions about these diagrams. So earlier I talked about indecomposability and how we can split up representations. And I mentioned that this allows us to characterize any arbitrary representation with just its indecomposable summits. And so if we're interested in studying this entire category of representations, we can just restrict our focus to the indecomposable representations. But we want to situate these indecomposable representations with respect to each other in some way. And so we're also going to look at the irreducible morphisms between these indecomposable representations. And when we write that down on a piece of paper, what we get is just a diagram with vertices and arrows. And we're going to call that the Auslander right quiver, which summarizes these indecomposable representations and the irreducible morphisms between them combinatorially and geometrically. For example, if we were to look at this quiver and we calculated all of the indecomposable representations, we looked at all the irreducible maps between these, what we would get is a diagram that looks like this. And so we've taken this enormously large and infinite category of representations, and we've distilled it down into this thing that we can write down on a piece of paper and just look at with our eyes. But this thing doesn't just pop out of nowhere. We still need to calculate it. And the tool that we use to calculate it is this thing called the knitting algorithm. The knitting algorithm takes as input an existing part of the Auslander right quiver and gives as output an extension of that existing part. More specifically, what it tells you is that if you have these three representations, M, N, and L, and you know that there exist arrows here, then there must also exist arrows here and a fourth indecomposable representation, which we'll call U, such that the dimensions of the vector spaces in the sum of N and L are the same as the dimensions of the vector spaces in the sum of M and U. But the knitting algorithm still requires some input to start with. So we need to actually start somewhere. We can't just apply the knitting algorithm to nothing and get an Auslander right quiver. So in more general form, the algorithm looks like this. We start by calculating the indecomposable projective representations. I won't get into too much detail about what these are, but anytime that you see anything highlighted in red for the rest of this talk, that's going to denote that what we're looking at is projective. Then you calculate the radicals of these indecomposable projectives, and you draw what are called the radical inclusions. And then you just apply the knitting algorithm to this bit of the Auslander right quiver until you reach the injective representations. Here I've highlighted in blue. That's going to follow the same pattern. Anytime you see something in blue for the rest of this talk, that will be injective. All right, let's look at an example, the one that we saw earlier. If we take this quiver, calculate its projective indecomposable representations, what we get is this. There are four of them. That corresponds to the fact that there are four vertices in our quiver. And when we draw the radical inclusions, we get a starting point that looks like this. Now, the knitting algorithm tells you that there exists an arrow here and an arrow here and an indecomposable representation here. So what is that indecomposable representation? Well, we can imagine doing this by just pulling this representation out of this. Covering another doesn't really work well on a projector. But you can see that we have a 3, a 4, and a 2 left over when we do that. And that's what we're going to have over here on this side of the mesh. And now we can apply the knitting algorithm again. We have an arrow here, here, and here, and that gets us this. And we just keep doing this process until we reach what are called the injective representations, as I've highlighted here in blue. So that's the end of the background. That was a lot of information. let's stop and summarize for a minute. Quivers are these diagrams from which we can make representations by assigning vector spaces to the points and linear maps to the arrows. We can restrict the representations by enforcing these rules that we call bounds on the path structure of our quiver. And we can characterize these representations using their indecomposable summons. Information about the indecomposable summons is summarized in the outside and right in quiver, which is then calculated via the knitting algorithm. So we can now start talking about the question that I've been working on for the past 6 months. I mentioned earlier that bound quivers have always seemed kind of weird and unintuitive to me, because the advantage of a quiver is that it's this very intuitive, very geometric visual object. You can look at it and immediately make statements about its structure without needing to do any math. And placing a bound on a quiver kind of removes that. Now, all of a sudden, you need to actually calculate things after you look at it in cases that you wouldn't otherwise need to if you didn't have a bound. And so what I'm interested in is taking bound quivers and figuring out how we can realize geometrically the effect that the bound has on the path structure of our quiver by rewriting it as some other unbound quiver. So let's look at this example. We've seen this quiver a few times before, and we're going to place this bound on. We're going to say that the path alpha 1, alpha 2, alpha 3, that's equal to 0. So we're going to get rid of this top path over here that goes from vertex 1 to vertex 4. So what does this really do for us? Well, you'll notice that that path was in some sense maximal. It's not contained properly in any other path in this quiver. And so when we enforce this bound, we're really only removing that one path. Nothing else gets set to 0. But we also want to preserve all of these subpaths, all these length 1 paths that are just the arrows, and all the length 2 paths. But we still are not allowed to go all the way from 1 to 4 in this top path. To me, what this feels like is we're separating the paths coming out of 1, but not going all the way to 4. And we're separating those from the paths going into 4, but not starting all the way at 1. So I've drawn these here. In blue, we have the paths going out of 1, and in red, we have the paths going into 4. But this still isn't really indicative of the structure that we are trying to understand. So what we have to do is we need to fully separate these. We need to pull these apart, kind of like a drawbridge. And now we end up with this new quiver. And this thing is actually really nice. I haven't talked about this in this talk, but if you flatten this down, what you get is just a straight line. And so this falls into a classification that we would call a Dinkin A-type quiver, and it's the simplest possible type of quiver. We have complete information about these, and we can take basically everything about them for granted. And so we've related this original difficult bound quiver to something that is much, much easier. And it turns out that when we look at the categories of representations of these two quivers, they are, at least on the surface, very similar. When we calculate the outside and right quiver of that original bound quiver, which I'm calling Q here, what we get is this. And these pictures are also on you guys' tables. If you want to look at them up close, they're kind of squished down here. And on the right, what we have is the outside and right quiver of that transformed quiver, that A type. Clearly, just superficially, they're the same shape. There seems to be a strong similarity here. And that's what we're going to look into. But first, we need to expand our view a little bit. We're not just interested in looking at a single quiver and seeing how that behaves. We want to look at an infinite class of quivers, of bound quivers, and see how we can work with these to transform them, to deform them into a simpler type of quiver. So what we're going to do is we're going to take that quiver we had before, we're going to expand that bottom path as much as we want, and then we're going to expand that top path as much as we want, and then we're going to bound out that top path. But we still have this source vertex over here, and this sink vertex over here, and this top path that is getting removed that is, again, in some sense, maximal. It's not contained in anything else. And we're going to transform this, just like we did before, into something that looks like this. And again, these pictures are also on all the tables. I don't expect you guys to absorb all of this in just a couple of seconds. But we're going to transform it into this thing. And again, this is just a straight line if we flatten out these two arms. So this is an A-type, and we can take all the information about this basically for granted. And our main question is, what sorts of similarities can we draw between the representations of the bound quiver and the representations of the transformed quiver? We're going to answer this in two different ways. The first is a theorem of Ari Pincus-Kazmar in 2025. which says that the outline array in quivers of Q and Q prime, I forgot to mention this, but that original bound quiver, I'm going to be referring to that as Q, and that other transformed quiver, that'll be referred to as Q prime. The outline array in quivers of these two have the same shape, but this is kind of a loose, like, intuitionist, not very mathematical statement. And so we're going to make this better by giving an explicit construction of the outline array in quiver of Q from that of Q prime. And how this works is we're going to follow this process. We're going to calculate the outline array in quiver of Q prime, writing each of the representations in that in shorthand notation. Then we're going to look at each of those representations, find every representation that has been duplicated when we do this transformation. That will be denoted with this little prime on that vertex. And we're going to get rid of that prime. We're going to replace that with the original vertex that it came from. The result is precisely the outline array in quiver of our original bound quiver. So let's talk about this combinatorial step first. This thing about the AR quivers having the same shape. So how do we show that two things have the same shape? Anybody got any guesses? I won't let you guess, because this is how we're going to do it. We're going to first start at the edges. We're going to show that the left-hand borders of these two shapes have the same shape. And then we're going to go to the other side, and we're going to look at the right-hand borders, and we're going to show that those are also identical. And then to fill in the space in between these two borders, we're going to show that the widths, or the lengths of each of the rows in the outline array quiver, those are also the same. So, like I said before, we can kind of take information about this transformed quiver for granted because it's what we call an A-type. And so we can immediately know that the outline array quiver is going to look like this. Now, there are some vertices here. This is just a toy example. I don't want you guys to think about this as being to scale, but it's going to generally have a zigzag over here. It's going to have a mirrored zigzag over here, and then it's going to be filled in with some width that depends on the number of vertices in it. And when we try to calculate the outline array quiver of our bound quiver that we started with, what the knitting algorithm tells us is first calculate the indecomposable projective representations, draw those radical inclusions, and then knit. But when we do that, we end up with this, and this is not what we're wanting. This is not what we expect based on what the outline array quiver of the transformed quiver looks like. And so it turns out there's actually some missing information that we need to pinpoint by cross-referencing with the indecomposable representations of the transformed quiver. And what that tells us is that there's going to be another diagonal over here, just like that. I'm not getting into the proof of this because honestly, it's a lot of very rote calculation. But what we find is that this left-hand border really does look the exact same as what we want it to be. And so now we have to do the right-hand border. And we could just repeat this process with the injective representations, but there's a very nice property of this quiver that is its own self-opposite, which means that if you reverse all of the arrows in this quiver, what you're going to get is the same structure, just with a relabeling on the vertices. And corollary to that is that the right-hand border of the outline array quiver is what we would call dual to the left-hand border. And so we can imagine this geometrically as just a mirror image. And with a few more calculations that I'm not going to get into, we find that the widths are the same and that these outline array quivers really do have the same shape, whatever that means. Because clearly these aren't actually the same. If we go back to these figures and we look at these, there are some very obvious differences here. Right away, we can see that, first of all, there are only 4 indecomposable projective representations here, whereas over there are 6. Took me a second to count, math major. And we have the same property for the injective representations. We just have more over here with the transformed quiver. But if you look even closer, and it probably doesn't show up on the screen, but if you look at this corner of the outline array quiver, the bound quiver, and then you look at its mirror image on the other side, those are the exact same. There are these repetitions appearing when we calculate this outline array quiver that aren't occurring over here. So evidently there's some kind of redundancy here, and we want to explain why that's happening. And if we go into this top row, the outline array quiver, with even more calculations, we can really confirm that these repeated representations really do exist. The knitting algorithm is giving us something that is repeating. It's kind of cyclic in nature. And if we apply the knitting algorithm from this top row down, what we get is that there are repeated representations on the next row of the AR quiver too. In fact, if there are n up here, then there are n minus 1 up here. And you keep doing this process, and each time we go down a row, we lose some repeated representations until it tapers off and we don't have any more. And so visually, what that looks like is we have a little triangle over here, and we have a little triangle over here of representations that are the exact same. We'd like to be able to describe this redundancy going in the opposite direction. We'd like to start with the easier indecomposable representations of the transform quiver and see how those explain why there's this redundancy that we're seeing in the indecomposable representations of the bound quiver. So to do this, what we're going to do is undo what we started with. So we constructed this transform quiver from the bound quiver by unfolding this top half, just like this. We saw this a little while ago. We end up with these duplicated vertices, 2 and 2 prime. These kind of have the same role, but we need to split them up to make this make intuitive sense. We have a similar thing going on with 3 and 3 prime and alpha 2 and alpha 2 prime. And so what we're going to do is we're just going to fold this path back in onto itself, combining these repeated vertices and combining these repeated edges. And to do this mathematically, what happens is we construct a mapping from the category of representations of the transform quiver, which remember is in some sense the easier one. It's the one that we know more information about. We're going to send the representations and morphisms in that category to the representations and morphisms in the category of representations of our original bound quiver. So if we think about having some arbitrary representation of this, how could we possibly work with this and combine it to get something that has this half folding back in onto itself? Well, if we have a specific representation, we're going to have some vector space here, some vector space here. So what we're going to do is we're going to look at vertex 2 in the original bound quiver. We're going to take the sum of the vector space here and vector space here. We're going to put that sum at that corresponding vertex in the bound quiver. In symbols, that's what this is. We're going to send mi to mi plus mi. We're going to do a very similar thing with the maps inside of each quiver. We're just going to, if there's a duplicated arrow, we're going to take the map at this original non-duplicated arrow, and then this one, and we're going to stick it into a 2x2 block matrix, again, just to make the dimensions work out. But categories also have morphisms. So we need to send the morphism somewhere. We're working as, if we're working between categories. And so we do the exact same thing, basically. We just bump up the dimension of these matrices, of these linear maps, to make sure that everything works out nicely. And it turns out that this mapping has some very nice properties. The most important one for us is this. In words, we would say that this functor, this mapping F, commutes with direct sum. So if you give me two representations of the transform quiver, and you combine them together with direct sum, and you look at where F sends that, that's going to be the same as looking where F sends one of them, and where F sends the other one, and then taking the direct sum of both of those. And from this, we can get a few more nice properties. We find that F preserves indecomposability. So the image of an indecomposable representation under F is also going to be indecomposable. And we have the same thing for irreducibility. And finally, we show that this thing is surjective, it's onto, that it really does hit every representation and every morphism in this category. And what this tells us is that we can restrict our focus to just how this mapping acts on the Alexander Rayton quiver of Q prime. We know that if we take an element of the Alexander Rayton quiver, it'll either be an irreducible morphism or an indecomposable representation. But these properties tell us that indecomposable representations and irreducible morphisms always get mapped to indecomposable representations and irreducible morphisms. But we can do even better than that. We can say that they map precisely onto the indecomposable representations and irreducible morphisms of our original bound quiver. And so we can imagine this mapping as this almost physical, this very tangible transformation of the surface, this geometric object that is the Alexander Rayton quiver. And we can just look at what that does. And again, this is very useful because we can restrict our focus from this enormous, infinitely large category to just this finite thing we can write on a piece of paper. So does this solve the problem that we had before? Does this describe the redundancy? Well, it turns out, yes. If we look at where we expect representations to occur, as we saw a few slides ago, we want them to happen here and here. And so if we focus on a corresponding representation in each of these corners, let's look at 2 prime, 3 prime, and also 2, 3. When we look at where F sends them, it's just the exact same thing. As we fold this path in on itself, we get this representation coming from both directions. And if we do some notational tricks and we see how this acts on these shorthand notations, what we find is all it does, it removes the primes from I prime, and we have that second result that we were looking for. So this is a nice correspondence, but there are still a lot of unanswered questions for us. One similarity that we can describe between these quivers that we didn't talk about in this talk is that if we look at the path algebra of our bound quiver, it's isomorphic to a subalgebra of the path algebra of the transformed quiver. And we know that we can describe the representations of a quiver via the modules over its path algebra. And we actually do have a pretty good method for describing the modules of a subalgebra from the modules of the full algebra. But it's very abstract, and it's hard to really describe precisely what it does in a specific case. And so something we're interested in looking at is how this compares to this other method that we call restriction of scalars. Are they identical? Does one of them do in some way better than the other? Does one of them do worse than the other? And so on. We're also interested in being able to more precisely pinpoint what information is preserved and lost during this transformation. If we have some sort of invariant of our original quiver, is that necessarily also an invariant of that transformed quiver? But ultimately, the really big question in my mind is whether or not this technique works for other bound quivers. The proof techniques that I've used in showing these two theorems rest fairly heavily on some major assumptions that we made about these quivers. One, we've assumed that they're acyclic. And this is very important because it allows us to restrict the number of indecomposable representations of our quiver. And we've also assumed that there are finitely many indecomposable representations. And that is, in general, not something that you can assume. And so we're interested in seeing whether or not the proof techniques that we've used can extend to other bound quivers with cycles and without finitely many indecomposable representations. So before I wrap up, I want to say a big thank you to everybody in the MSCS department. I think I've had a class with every single professor in the math department at the school, and every single one of them has been amazing. So thank you to everybody. And also a big special thank you to my advisor, Yari, who's been infinitely supportive and patient with me through all of this project. Thank you, guys.
Any questions for Ari?
Adam.
I don't want to be like that guy, but quivers in general, what is like the mathematical advantage? Because like my understanding is representations, you usually want to kind of understand an abstract algebra and physically what does it do?
Well, the importance of quivers lies in the fact that they're so intuitive. You can look at a quiver and immediately get properties of it, but if I write down some really formal definition of some arbitrary finite dimensional associative K algebra, you're not going to be able to immediately intuitively pick up on information about it. And I very briefly mentioned this, but one of the really big advantages of quivers is it lets us count the indecomposable projective and injective representations, again, with the very big assumption that our quiver is acyclic. So if I give you this quiver, its path algebra is isomorphic to something like maybe it's something like this. But the point is, when you look at this, even if you've taken abstract algebra, this doesn't really mean that much to you. There are certain things you can tell me about it, but if I asked you how many indecomposable projective representations of this are there, you would not be able to answer that question immediately. But if you look at this quiver, you can say, all right, well, it's acyclic. There are 3 vertices. There are 3 indecomposable projective representations. I hope that answers your question.
Thanks for a fantastic talk, Ari. Can you speak a little bit about like what starts to break down in terms of the cyclic nature? Because like my basic intuition is that like you're gonna try to make these, like representations of these numbers, which then like does it end up being these like infinite stacks of numbers because you have to keep going around the cycles, or like is that kind of what's going on there? What's the vibe on the cyclic things?
The one sentence answer is that the path algebra is infinite dimensional, and sorry, Ori, but I don't like that. And so in order to like glean information from it, quote unquote, easily, you need to really restrict the dimension, but then you lose all of the information. I shouldn't say all, but a lot of the information an arbitrarily large amount of the information contained in that cycle of the quiver. Yeah, so that's the answer. Adrian?
I have a question actually about this, interpretation, like ring interpretation of the path algebra. I guess so this is like over some, like linear combination that's been set equal to 0. That's what's being quotiented out by. I'm curious, like, what ends up being in this ideal in the ring context? Or I guess, like, what can you say about the structure that happens to the ring when you quotient out by this ideal?
It's hard to say really precisely what happens to the structure of the ring, other than just, well, it becomes a quotient. And really that just depends on the ideal that you're quotienting out by. But there are some nice intuitions about the diagram. And again, this is the whole advantage of using this paradigm in the first place. We can just look at the diagram and get information from that. So I hope you guys can see this. This marker is really new, and so it writes very thinly. If we bound out this, we can immediately describe how that changes. I'm talking about this a lot, but we can immediately describe how that changes the indecomposable projective representations. Because I didn't talk about this in my talk, but the way that we calculate those indecomposable projective representations is that we look at a vertex, we pick that vertex, we look at all the paths emanating out of it. And if we bound out this top, if we bound out this top path, what happens is we lose one of these paths emanating out. I hope that answers. Ben?
I have a question about this functor.
Yeah.
You showed that the is it called direct sum of m and n is isomorphic to functor on n and the functor on n.
Yeah.
Are m and n both bound quivers in this case?
M and N are representations.
Okay.
So if we go back to the definition of this mapping, we start at the category of representations of the transformed quiver.
Mhm.
That's this,
Yeah.
this one. And so what this mapping does is it sends representations, this direct sum is a representation, to a representation of the transformed quiver. So the argument of this is always going to be a representation or a morphism of our original bound, or I'm sorry, our second transformed quiver.
Okay. But like, are the things that m and n are representing, are those are they representations of quivers? And are they both bound quivers? The things that they're representing?
No, we
Okay.
start with the transformed quiver. This
Yeah.
is unbound. This is
Okay.
A type.
Okay. So it sends it to the quiver.
Yes.
Okay.
Exactly. Andrew?
All right, thank you. Question maybe building off that, the quiver you have up there, so if you had another arrow going from 4 to another one, say 5, could you add that for me? Could your result say something about that structure,
We hope.
or
Um,
or likewise lead again, you know?
This is one of the, yeah, I mean, I told you that this is really, in my mind, the big question. But the issue is that when you try to do a transformation on this, what you end up with is something that looks like this. Now,
This doesn't give you a.
off the top of my head, this is not finite representation type, which means it doesn't have finitely many indecomposable representations. Okay, I take it back. But if you added a whole bunch more, you could make it big enough that it wouldn't be finite representation type. And so this technique wouldn't work in that.
Other question.
I want to ask you about the knitting algorithm. You said that like you kind of like got rid of this 3. It's kind of the intuitive way of describing it.
Yeah.
But you only got rid of the bottom 3. And it didn't matter that it was on the bottom in your kind of shorthand notation.
Yeah, in this case, no. And the reason for this is because this is a simple representation. And I say that, when I say that, I mean 2 things. 1, it's very simple to work with. And 2, it is in a algebraic categorical sense, simple, meaning it only has a 1-dimensional vector space in one place. But if you were to have something else, like let's say that this was, let's say we have like a 5 here and we have 5 here, and then we have 5 here. Intuitively, and this is not a rigorous thing to do, but intuitively what you want to do is you want to take out the one that best matches this. Here you have this thing between 3 and 5. Here you have nothing between 3 and 5. You would want to take it out of that one. But in general, it doesn't really matter which one you take out.
But you only take it out of one usually?
Yes.
What I'll add to that is essentially you have a relationship between dimension vectors of your representations. And there is a way to say like which one you should take it from, but it depends on like the maps and like sometimes you don't actually care. It sort of depends on whether you care about the maps or not.
The knitting algorithm is a highly imperfect tool anyway,
Okay,
so it's up to interpretation.
all right.
Ari, can you put up the picture of Q and K, is that what it is? But then the quiver, yeah, Q and K, the quiver, you've got a picture. I'm curious about N and K.
Mhm.
If you have another one where N plus K is the same, but is the sum of N and K what matters here, or does it change, like if N is really K, if I shrink K by 1 and add 1 to N, how does it do, what happens?
So there are some cases where it's only the sum that matters. But in general, those cases are unbound quivers. The important thing is that here we have a bound on one of the paths. And so if we have like huge paths over here, we subtract 10 billion from this and add 10 billion to this, the bound will be significantly different. And also when you do this transformation into this A-type, the A-type will also be significantly different.
Isn't the A type the same if N and K are equal?
No, the lengths of these paths, these
Oh, I
arms, depends on N. This depends on K. And actually, the size of this depends. The size of this is, you can write it down as 2N plus K minus 2. So you can see it doesn't grow equally in N and K.
Go back to Andrew's question. If Andrew drew the loop with the one, and it almost could be type D if it's small.
Yes,
In that very small case, does it work? You
Uh,
did D3 or something?
we haven't actually looked at that. But
Yeah,
I
we
would,
looked at
I
for,
would
like,
really
half of
expect it to. Almost certainly would.
Yeah, you could definitely get D and E type and then kind of do something there, but again, like once you get big enough, it's like, okay, you're kind of out of it.
And maybe the E-types are nice because there are finitely many E-types with finite representation type, but the D-types are going to be more difficult because you can't get this entire infinite family, or even like a nice portion of it, a nice infinite portion of it using this type.
All right, let's maybe call it there.
Really.
38 minutes.
You wanna stop you can stop the recording.
Oh, yeah. All right, well,